Hi there, my name is Karen Calderon Moreno. I am a master's student at the University of Alberta, working under the supervision of Dr. Gonzalo Zambrano and Dr. Richard Laturnik in the Reservoir Geomechanics Research Group. I am really excited to share with you my research, which is THM modeling to evaluate the joule-thomson cooling impact in a thin, highly depleted gas reservoir in Alberta. As a background, we know that carbon dioxide capture and storage in geological formation is considered one of the most promising methods for reducing large-scale CO2 emissions into the atmosphere. The primary objective is to sequester CO2 in underground reservoirs or structures such as oil or gas reservoirs, saline aquifers, and coal beds. Keeping the CO2 safely stored for many years to reduce greenhouse gas emissions and mitigate the impact of global climate change. Carbon capture and storage projects could play a significant role in helping Canada meet its greenhouse gas emissions reduction target under the United Nations Framework Convention on Climate Change. Alberta, with its large industrial operations and greater CO2 storage capacity than countries like Norway, Korea, India, and even twice that of the entire Middle East, is an early leader in developing CCS hubs. In 2022, the Alberta government selected 25 new commercial CCS projects. However, just only 2 projects, one in Alberta with Shell and another one in Saskatchewan with Aquistor, received license to proceed with development of CCS in saline aquifers. On the other hand, we know that depleted gas fields are among the most promising targets for CO2 storage due to their proven capacity, sealing structures, and existing infrastructures which might be reused. This enhances confidence in storage security and offers potential cost savings. For the purpose of my research, we have that during CCS projects, CO2 is typically injected in a supercritical phase at high pressure and moderate temperature. This contrasts with depleted gas reservoirs, which often have significantly lower pressures. Due to this difference in pressure, the CO2 could lead to a cooling effect in the reservoir. This cooling effect is known as the joule-thomson cooling effect. Understanding and mitigating the joule-thomson cooling effect is crucial to preventing the formation of ice and gas hydrates during injection, which could set operational challenges. The joule-thomson cooling effect during CO2 injection in depleted gas reservoirs requires extreme caution due to its safety implications and the potential impact on the long-term success of CO2 storage. Sudden cooling can reduce reservoir temperature, leading to stress changes in the rock. This can result in thermal fractures, which might be compromising the integrity of the reservoir and the well. The primary objective of this research is to evaluate the technical feasibility and assess potential leakage risks associated with CO2 storage in an onshore, pressure-depleted gas reservoir located near Exxon in Alberta, Canada. This study will explore different injection scenarios to understand the cooling effect's impact on the reservoir's thermoporolastic response, which can cause stress reduction within the reservoir and potentially lead to the formation of thermal fractures. Now, I'm going to talk about the methodology that I'm going to follow. First, I will need production and completion data for the wells that are in my field. For this data, I'm going to download it from GeoScout. Also, I will use the static model of my field that was built in Petrel. Having this data and files available, I'm going to import them in CNG using the module gem, a compositional module. With this data in CNG, I'm going to do the history matching for my production and pressure data from 1958 to 2024. Along with, I will use core samples that I got from the Alberta Energy Regulator. I was able to pick up and select 11 core samples at different depth and for the different formations that are in my well. These formations are Chunda, Elton, and Nordic. Having these 11 core samples in the lab, I got 61 small plugs. These 61 plugs, I'm going to be using it to test the thermal conductivity and thermal diffusivity for the formations at a different depth. For this, I am going to use the Cither equipment and an oven. First, I'm going to start looking at the thermal conductivity and diffusivity at room temperature for my 61 samples. Then I'm going to measure the thermal conductivity and thermal diffusivity of these samples at reservoir temperature, that is 98 Celsius. For this, I'm going to use an oven together with the Cither equipment. After that, I'm going to build my CO2 injection model. For this model, I'm going to be using just the well under study. And this model, I'm going to limit it to be 1,000 meters around the well that I'm going to be working with. Additionally to that, I'm going to add the cap rock and the lower reservoir formation. After that, I'm going to use a squat go cap to create the geometry that is going to be compatible for both models, for my flow model and for my mechanical model. I need this because the pressures and temperatures are affecting the stress and the displacement, and these changes need to be passed to my mechanical simulator. And then in my mechanical simulator, the resulting strain are going to be used to calculate the new permeability, and this new permeability need to be passed back to my flow model. That's why I'm going to use the squat go cap to build a geometry compatible for both simulators. With the platform RG coupling, I'm going to couple my two simulators, my mechanical simulator and my flow simulators. That in this case, for my mechanical simulator, I'm going to use FLAG 3D, and from my flow simulator, I'm going to use GEM CNG. Coupling these two simulators is going to allow me to run my models sequentially, helping me to reduce time. Also, this is going to allow me to evaluate the joule-thomson cooling effect at different scenarios. For the respective result, so far I have results from the lab and initial result for my history machine. For the lab, I had finished the measurement of my thermal conductivity and my thermal diffusivity at room temperature. So here in the plot, you can visualize the thermal conductivity and thermal diffusivity for the 61 plugs that I have that are radial and axial plugs and at a different depth, and you can see for the formations and the depth that they belong. For my simulation part, I finished the first run for my history machine, when I know that the discovery pressure of my field is 26.8 MPa and that the current depletion pressure is 2.1 MPa. However, for my first simulation, I got that the depleted pressure is 6 MPa, which means that I still have room to enhance my history machine model. For the future work, on the ongoing work, I'm going to start looking for the thermal conductivity and diffusivity at reservoir temperature. That means that I'm going to run the test that I already did at room temperature and reservoir temperature with the help of an oven and the Cither equipment. For my simulation part, I need to improve my history matching model to try to make it as close as the real conditions of my field, that is 2.1 MPa for pressure. Additionally to that, I plan and I hope to build different CO2 scenarios where I can visualize the CO2 phase properties, stresses, and thermopolar elastic response. Also, together with the CO2 plume development in the reservoir at these different scenarios. For the CO2 plume development, our guess is that this plume is going to have like a piston effect, because keep in mind, it's a really thin reservoir. So when the CO2 get into the reservoir, it's going to be just going through of it, and we won't be able to visualize a really like a plume movement inside the reservoir. Together with this, I hope and I plan to be able to visualize the reservoir's proper distribution for the different scenarios that I'm going to have, having the plus of the pressure distribution, temperature distribution, and minimum effective stress distribution at different injection periods and at different injection rates. The same plots that I had here as an example, but these plots belong for a different research. With these plots, I'm going to be able to visualize the impact of the cooling effect in the reservoir. That is my main target in this research. That's everything for now. If you have any questions or any suggestions for my research, please don't hesitate to contact me, and thank you for watching.